Okay, chapter 3.2, we'll be going over polynomial functions and their graphs. So before we get into graphing it and the steps for graphing it, let's just look at what the actual definition of a polynomial function is. So for a polynomial function for this, let's let n be a positive integer, so 1, 2, 3, 4, and so on. And all of these little a's are going to be real numbers. So the function f of x equals this whole nasty looking thing. This would be a polynomial. So all of these a's are just real numbers, and all of these exponents are going to be positive integers. Okay, so we say that this is a polynomial function of degree n, because that's going to be the largest degree on the polynomial for the variable. So we call those degree n polynomials. And that coefficient on the variable with the largest exponent is called the leading coefficient. And the term with the largest exponent is called the leading term. So for some examples of polynomials, we could have something like f of x equals negative 2x to the fifth minus 4x cubed minus 1. So that would be a polynomial function of degree 5 because that's the largest exponent. For another one, say g of x equals 3x to the fourth plus radical 2 times x to the second. And this would be a degree 4 polynomial because that's the largest exponent on the variable. And then for one more, could be something like negative 3x to the fourth times x minus 2 times x plus 3. So this one looks a little different, right? Because this one is factored. It's not all expanded out. So we could still figure out the degree for this. The degree is going to be, this first one up here is 4. The next factor has a degree of 1. So does the third one. So when we're multiplying common bases, we're multiplying variables with the same base, we add the exponents. So the total degree that this is going to have is 4 plus 1 plus 1, which is going to be a degree of 6. Okay, you can also see in example A and B how it's organized where the variables are in descending order for the exponents, and that's called standard form for a polynomial. So some examples that are not polynomials, something like f of x equals negative 3 radical x plus 2x squared minus 5. So that's not a polynomial because of the radical x. We know that that equals x to the 1/2. 1/2 is not a positive integer, so that's not a polynomial. For the next one, let's say we have g of x is negative 2. Let me write this a little differently. Negative 2 over x squared plus radical 5x plus 3. So this is also not a polynomial because that variable is in the denominator. We know that if we have something like 1 over x squared, that's x to the negative 2. Negative 2 is not a positive integer, so this is not a polynomial. We'll do one more. So let's say h of x, 2x squared minus 4, all divided by x cubed minus 2x plus 1. So this is actually, since there's that big division sign here, that's actually something called the rational function that we'll get into, but that's also not a polynomial. There's a polynomial in the numerator and denominator, but the whole thing itself is not a polynomial. Okay, so some important properties of polynomials. Every polynomial is going to be a smooth function. So smooth in math means essentially that there's only rounded curves. There's no sharp corners. And polynomials are also continuous functions. So you can draw them without picking up your pencil. There's no breaks or there's no holes in them or no jumps. And the domain of every polynomial is all real numbers, so negative infinity to positive infinity. So some examples of what they might look like here. For something that is a polynomial, it might look something like this. So they're always going to have arrows on the end. So we can see that this is a smooth function because it's only rounded corners. And something that's not a polynomial might be something like this. Okay, so we can see that right here it is discontinuous, meaning it cannot be a polynomial. And right here there's a sharp corner. These sharp corners are called cusps. So there's two things that made this not a polynomial. Okay, so let's go over the types of polynomials. So we've done a bunch of these so far. We've seen a bunch of them up to this point, hopefully. I'm going to go by degree. So degree 0 polynomials, those are called constant functions. So remember, degree is referring to the largest exponent on the variable. So if we have something that's a degree 0 polynomial, that would be something like f of x equals c, where c is a constant. It's just a number. So that's something like f of x equals 3, let's say. So if it was f of x equals 3, that would be a horizontal line. So degree 0 functions, constant functions, are horizontal lines. So next, degree 1 polynomials. Degree 1 polynomials are degree 1 polynomials are linear functions. So we can write them in the form f of x equals mx plus b. You could write it as ax plus b. I'm just putting it in this slope-intercept form that we're used to seeing, with m being the slope of the line, rise over run, and b is the y-intercept. So hopefully we remember working with these. So graphing a line, I'm just going to kind of put something really random. It might look something like that, where you could find the y-intercept and then also use the slope to find a second point and then just graph the straight line. Degree 2 polynomials are quadratic functions, so we did those in section 3.1. I'm writing all of these in standard form also. So quadratic functions, f of x equals ax squared plus bx plus c. So we know that these look something like that, parabolas. So this is general form of a quadratic. But overall, it's standard form of a polynomial, so a little bit confusing with the terminology. Okay, and for the cubic functions, a cubic function would be, we'll see that it starts to get a little bit ridiculous. Something like ax cubed plus bx squared plus cx plus d. So degree 3 polynomials, cubic functions might look something like this. So you can kind of see how I'm doing these turning points here, and we'll get to that in a little bit and why I'm graphing it the way I'm graphing it. And the last one for now, a quartic function. These are degree 4 polynomials, and you'll see why I stopped on this one. So that's something like ax to the 4th plus bx cubed plus cx squared plus dx plus e. So obviously all of these a, b, c's and everything are constants, and the x's are the variables. So degree 4 might look something like that. And then I put and so on down there just because we can have degree 5, degree 6, degree 1 million. I can keep on going. Okay, so let's look at the end behavior of polynomials. So the end behavior, when we refer to the end behavior, it's what's happening to the function as we go to the far left and to the far right of the x-axis. So if we're going to the far left, that means as x goes to negative infinity. And if we go to the far right, that means as x goes to positive infinity. And what we're going to be doing, we're going to be using something called the leading coefficient test to determine the end behavior. So the idea for the end behavior of polynomials, as x goes to positive infinity or x goes to negative infinity, so as it increases or decreases without bound, the polynomial function, just that big nasty looking function, will eventually continue to rise or fall. So what that means is that it's either going to go to positive infinity or negative infinity. So as x goes to positive or negative infinity, so will the y values, so will the function values. Okay, so there's going to be 4 different cases here. So what we have to do is we have to look at the leading term. I'll write that down. We're going to look at the leading term, so we're going to be using this term right here, the a sub n x to the n. So we go to the term with the largest exponent on the variable, and we know we're using that one. So what we're going to do is for that leading term's exponent, either the exponent is going to be even or odd, and either the leading coefficient out front is going to be positive or negative. That gives us 4 different possibilities here. So if we have an odd exponent and the leading coefficient is positive, what that means is that the graph is going to fall left and it rises right. So what that means is that if we went all the way to the left on the x-axis, eventually it would fall like that. I'm going to put dotted lines in the middle saying we don't know what's going on in the middle, we just know what's going on at the end. And then it rises right. So it would look like that at the end of the functions graph. So an example for this might be something like f of x equals x cubed. Hopefully we know what that looks like. That actually almost looks exactly like that red mini graph that I just drew there. Okay, the next case is if we have a leading coefficient that's negative. So odd exponent, leading coefficient that's negative. That means the graph is going to rise left and falls to the right. So it's pretty much just the opposite of what we just did. So it's going to look something like this, where it rises to the left, dotted line for something happening in the middle, and then it falls to the right. So an example for this might be f of x equals negative x cubed. So we can see the negative out front, negative coefficient, odd exponent, so it would look something like that at the ends. So next, if we have an even exponent, so now we'll do the even exponents. Even exponent and a leading coefficient that's positive, that will be graph rises right. Graph rises right, and it also rises left. We should be more familiar with these ones because of the quadratics. So that means it rises to the left, and then it does some stuff in the middle, and then it's going to rise to the right. So like I mentioned with the quadratics, an example would be something like x squared. F of x equals x squared. We know exactly what that looks like. That's a parabola opening upwards. So rises left, rises right. For the last one here, if the leading coefficient's negative with an even exponent, that's going to be the graph. Oops. The graph falls right. And it also falls left. So that would look like an example would be a parabola opening downwards, falling to the left and to the right. So an example for this would be negative x squared, which we know what that looks like, parabola opening downwards. So you can see that when the exponent's even, it's doing the same behavior on both ends. When the exponent is odd, it's doing opposite behavior on the ends. So let's do some examples here. So let's use the leading coefficient test to determine the end behavior of the following functions. So we have f of x equals x cubed plus 3x squared minus x minus 3. So the leading coefficient, the leading term is going to be x cubed. So we literally look at nothing else here. So the reason why we look at nothing else here to tell us what's happening as x is going towards positive or negative infinity, we only look at the largest term because when x is really big, imagine as x is going to be like a million here, 10 million, 2 trillion, it's getting larger and larger. That term with the largest exponent is going to overpower every other term. So that's why we only have to look at the leading term for this test. So the leading term here is x cubed. So we have an odd exponent, and we have a positive coefficient because there's a coefficient of 1 out front. So what this means is that if you just wanted to remember or memorize what happens based on those previous pages of the 4 scenarios, then what this would tell us is that this is going to fall to the left and rise to the right. So falls left and rises to the right. What I recommend doing, you don't have to do it this way if you don't want to, f of x equals that polynomial function right there. The leading term is x cubed. That means on the ends it's going to look like x cubed. So we should know what x cubed looks like, so we should know that it falls left and rises right. For the next one, we have g of x is x to the 4th minus 4x squared. So the leading term here is x to the 4th. So this is going to be an even exponent. And once again, we have a coefficient of 1 out front, so that's a positive coefficient. So what that means is x to the 4th is going to look like, on the end, it's going to look like x squared, because that's an even exponent positive coefficient. So we know that it's going to rise left and then rise right. Or once again, just base it off of the last page. Okay, and then the next one, a little bit harder. We have negative h of x is negative 4x cubed times x minus 1 squared times x plus 5. So this one's factored. So we need to imagine this expanded out. So you could distribute everything and expand it out, but it's not necessary for this. All you have to do is let's look at the exponent first. This has an exponent of 3. This has an exponent of 2. This has an exponent of 1. So that's going to be adding the exponents together when we're multiplying them. So it's going to be 3 plus 2 plus 1. That's going to give us 6. 3 plus 2 plus 1 is 6. So that means we have an even exponent. And then next, for the coefficient we have a negative 4 that's going to be multiplied. We have to go to the variable in here. The variable has a coefficient of 1. So does this one over here. So it's going to be negative 4 times 1, which is going to give us a negative 4, which is a negative coefficient. If you really wanted to, like I said, you could expand that whole thing out. It really wouldn't take that long, but it's just unnecessary. So even exponent, negative coefficient, what I think of is negative x squared, which we know opens down. So it would be falling left and falling right. So falls left, falls right. And for the next one, for D, one more. P of x, so it's that long nasty thing, 3,776x minus 49x cubed plus 806x squared plus 2,503. So this one is not in descending order in terms of the exponents. So our leading term is actually right there this time. It's actually negative 49x cubed. So just because it's called the leading term doesn't mean it's the first term. It means it's the largest variable. So we have a odd exponent and we have a negative coefficient. Okay, so when that happens, that means it's going to rise to the left and fall to the right. So rise left and falls right. So I'm drawing it out like that and writing it out like this just to kind of drive home both points just so we know what I'm talking about when I write it out. Okay, so those are essentially the 4 examples that we can get, the 4 different scenarios that we can get for end behavior for polynomials, the only 4 different cases. Okay, next, so let's look at the x-intercepts for how we find x-intercepts. So x-intercepts, this goes for any function, but we're obviously just talking about polynomials here. What we're going to do is we set the function equal to 0, and we solve it for x. So finding where it crosses the x-axis, set it the whole function equal to 0 and solve for x. We can call those the x-intercepts, the zeros, or the roots. They all mean the same thing. So what we're going to have to do most of the time here is actually factor the polynomial. So really, really important to remember how to factor, and then apply the zero product property. And like I just said, really important, recall these factoring techniques. Greatest common factor, factoring a quadratic trinomial, grouping, and difference of squares. And another little note to keep in mind is that a degree n polynomial will have at most n x-intercepts. So if it was a degree 4 polynomial, it would have at most 4 x-intercepts and no more, but it could have less. So let's do some examples, and then I'll just graph them real quick just so we can see them. So we'll start off easy. F of x equals x minus 4. Well, if we wanted the x-intercepts, we set it equal to 0. So x minus 4 equals 0. Add 4 on both sides, we get x equals 4. So we should have known that because we should know how to graph f of x equals x minus 4. It's just a line. So the x-intercept is right here. Slope of 1 would look something like this. So it's a line. This is a linear function. And let's do one more linear one just to get the easy ones out of the way. So g of x is 3x plus 9. So once again, we want the x-intercepts. We're setting it equal to 0. So that's going to be 3x plus 9 equals 0. We're going to subtract 9, divide both sides by 3. We get x equals negative 3. So I obviously skipped showing the work for that, just because we should know how to do it. So negative 3 is over here. We have a slope of 3, y-intercept of 9. So this would be something like this. This is our g of x. Okay, let's make them a little bit harder now. So now we have a quadratic, so degree 2. So we have h of x is x squared plus 5x plus 6. So what we're going to do is we're going to set it equal to 0, set h of x equal to 0. And that's going to be x squared plus 5x plus 6 equals 0. So remember, when we're trying to find the quadratic set equal to 0, you're going to want to try to factor it first because that'll make it easier. If not, quadratic formula always works for quadratics. This does factor. It factors as x plus 2 times x plus 3, two numbers that multiply to 6 that add to 5, 2 and 3, both positive. And the next thing that we're going to do is the zero product property. So you can set it up like this if you want, you don't have to. So the only way something times something is 0 is if one of those are 0. So we set each factor equal to 0 separately, and then we solve them. So for the left-hand side, subtract 2 on both sides, we get x equals negative 2. Right-hand side, subtract 3, we get x equals negative 3. Okay, so those are our x-intercepts. So if we wanted to graph it, it would actually look something like this. So there are the x-intercepts. So it'd be a quadratic. So maybe something like that, not perfect, but good enough. Okay, and the next one we have p of x is 2x cubed minus 4x squared. So once again, we are setting this equal to 0. So 2x cubed minus 4x squared equals 0. So this time, remember the factoring techniques. This time we're going to need greatest common factor. We're going to need a GCF. The greatest common factor here is 2x squared. So make a little note that this is a GCF factoring. And then what we're left with, so remember we divided it out front. We're left with x for the first term minus 2 for the second term. So we have two different factors here. We have 2x squared. Set that equal to 0. And then x minus 2 equals 0. So that's the zero product property again. And then we solve them separately. We end up getting x equals 0 and x equals 2. So if we graph this, obviously we're going to get into other ways that, details that we need to graph it. We have our x-intercepts. This will look something like this. So you can see how right here at the origin, at that one, it doesn't cut through it directly. It touches it and bounces back the way that it came, and then it goes through at x equals 2. So there's a reason for that, and we'll get to that in a little bit. Okay, and then for the next one, we have g of x is 2x cubed minus 18x squared minus 20x. Okay, so we set it equal to 0. So 2x cubed minus 18x squared minus 20x equals 0. So once again, always think GCF first. It won't always be GCF, but think GCF first. So there is a GCF here of 2x. So I'm going to write down GCF. And we divided it out, so what we're left with inside here is x squared minus 9x minus 10. So we're not really done factoring yet. Let's keep on going. We can factor that quadratic in here, x squared minus 9x minus 10. Two numbers that multiply to negative 10 that add to negative 9. This would be x minus 10 times x plus 1. So your goal is to kind of get it down to linear factors if you can, meaning all of these factors are degree 1 on the variable. So now that we have all of those easy factors to work with, let's set them all equal to 0. So either 2x is 0, or x minus 10 is 0, or x plus 1 is 0. So we solve them all separately. We divide for 2x equals 0, divide both sides by 2, we get x equals 0. X minus 10 equals 0, add 10 to both sides, get x equals 10. X plus 1 equals 0, subtract 1 on both sides, x equals negative 1. So if we were to, I'm just going to plop these down on the graph on the right. We have, what do we have? Negative 1, 0, and 10. So if we were to graph this, it would look something like that. Okay, let's do a couple more just to make sure we know what the other factoring method. Okay, so we have x cubed plus 3x squared minus x minus 3. Okay, so for this one is a cubic. And it's a cubic with all four terms. It has the cube term, the squared term, the x term, and the constant term. So let's see what happens when we try to set it equal to 0. So setting this whole thing to 0. So originally we might think maybe we can factor out a GCF. There's no GCF here. That constant term of negative 3 kind of ruins that. What we have to do here is the factoring technique called grouping. So this is going to be grouping. This is really common with cubic polynomials with all four terms in them. So what we do is we group the first two terms together with parentheses. And then we group the second two terms. But since there's a negative x, what we have to do is put plus and then minus x minus 3. Because if we just put the parentheses after the negative, we'd actually be changing the expression for those two terms. So now what we're going to do is we go in each one of those set of parentheses separately and take out the GCF, factor out the GCF. So the GCF from the first one is going to be x squared, and then we're left with x plus 3. So our goal is to get an x plus 3 left over in the second one. To do that, we have to factor out a negative 1. So we get minus parentheses x plus 3. So the reason why we did that, the reason why that was our goal, is because now we can rewrite this by factoring out another main GCF of x plus 3. We're going to be left with x squared for the first term, which is right here. And then we're going to be left with minus 1 right there. So x squared minus 1. Okay, I'm going to factor x squared minus 1 using difference of squares. So x squared minus 1, it can be written as x minus 1 times x plus 1. So now it's completely factored. So what we can do is set all of those factors equal to 0. So x plus 3 equals 0 gives us x equals negative 3. X minus 1 equals 0 gives us x equals 1. And x plus 1 equals 0 gives us x equals negative 1. I'm just going to write down that this was difference of squares in here. Okay, so I'm going to plot these points. So negative 3, negative 1, and 1. So if we graph this and figure out the other information that we still haven't done yet, it would end up looking something like this. And this is our function f of x. Okay, let's do one or two more just to make sure we got, this is usually one of the hardest parts, that's why I have a lot of examples here. So for the next one, h of x is x cubed plus 2x squared minus 4x minus 8. So this is also going to be grouping. So finding the x-intercepts, h of x equals 0, x cubed plus 2x squared minus 4x minus 8 equals 0. So we're going to group these first two terms, x cubed plus 2x squared plus negative 4x minus 8. So we have to pull that same little trick that we just did. So the GCF from the first group is going to be x squared. We're left with x plus 2. So we need an x plus 2 left over in the next one, which means we have to factor out a negative 4, which would give us the x plus 2 left. So now we can factor out the x plus 2. And we're left with x squared minus 4. This is also going to be difference of squares for this next step. So x squared minus 4 can be rewritten as x plus 2 times x minus 2. So what I'm going to do here, we could set all of these factors equal to 0 right now, right? They're all linear factors. Since we have two x plus 2's being multiplied, I'm going to rewrite that as x plus 2 squared. And there's a reason why I'm doing it, which we'll get into in 1 second. So that's going to be setting these factors to 0, x plus 2 squared equals 0, and x minus 2 equals 0. The right-hand side will give us x equals 2. On the left-hand side, we would square root both sides, and then we would subtract 2. So we get x equals negative 2. Okay, and if we were to graph that, here's negative 2, here's 2. That would look something like that. Oops. Okay, so let's do maybe one more here. Yeah, just one more before we get into the next thing. So we have g of x is negative x to the fourth plus 4x cubed minus 4x squared. So that's going to be negative x to the fourth plus 4x cubed minus 4x squared equals 0. Okay, so what I'm going to do for this one is I'm going to factor out a GCF. So I'm going to write GCF first just so we know. The GCF I'm going to factor out, the leading term here has a negative in it, so I'm actually going to factor that out. So I'm going to factor out negative x squared for the GCF. We would be left with x squared minus 4x plus 4. A little bit trickier because we have to negate every term in the parentheses. That quadratic inside can be factored. Two numbers that multiply to 4 that add to negative 2, or negative 4, are negative 2 and negative 2. So we can factor that as x minus 2 times x minus 2 equals 0. And just like last time, what I'm going to do is I'm going to write those two factors together using an exponent. So that's going to be x minus 2 squared, since there was two of them being multiplied. And now I'm going to chop it up. Set that factor to 0, set this factor to 0. The one on the left, we can negate both sides and then take the square root. We would get x equals 0 either way. Right side, square root both sides, add 2, we get x equals 2. So 0, 2, and it would look something like that. And this would be our function g of x. Okay, so let's think back to the end behavior real quick. The end behavior for this function, if we looked at this first term, negative x to the fourth, that is an even exponent with a negative coefficient. That means it falls to the left and falls to the right. So that's how I knew to draw it falling to the left and falling to the right. The reason why I knew it didn't cut through at these x-intercepts and it hit them both and bounced back was because of these exponents on the factors. If it's an even exponent, that means it touches it and bounces back. If it's an odd exponent, that means it cuts through the x-axis at that x-intercept. So that's why I knew to draw it like that. And that is something called multiplicity, which we'll be doing right now. So the multiplicity of zeros, just like I just mentioned, it tells us if the curve is going through the x-axis at the x-intercept, or if it's touching it and turning around the way it came. So what we're going to do is, the way that I think is the easiest is to rewrite the function as a product of its factors. So that's why I was rewriting factors instead of like x minus 2 times x minus 2. I rewrote it as x minus 2 squared because that exponent tells us what the behavior is at the x-intercept. So the two types of multiplicity here for an x-intercept is there's even multiplicity and odd multiplicity, and it is directly referring to the exponent on the factor. So if there's even multiplicity, that means there's an even exponent on the factor, and that means it touches the x-axis and turns around at the x-intercept. So let's say we have an x-intercept right here, and let's say we know it does this. Let's say that's some function. Since it touches it, here's the x-intercept, it touches the x-axis and then turns around the way that it came, the function stayed positive, we would say the x-intercept has even multiplicity. For the next one, for odd multiplicity, that means there's going to be an odd exponent on the factor. That means it's going to completely cross through the x-axis at that intercept. So maybe something like this. So obviously it's crossing through right here. We would say this x-intercept has odd multiplicity. So let's do some examples here. So let's find the zeros, which means x-intercepts. Find the x-intercepts and the multiplicity of each x-intercept. So for the first one, we have f of x is negative x squared times x minus 2 cubed. So we want the x-intercepts, so we set it equal to 0. So we have negative x squared times x minus 2 cubed equals 0. So this is nice and factored for us already, so we can just use the zero product property and say, well, that either means negative x squared equals 0 or x minus 2 cubed equals 0. So we could, on this left-hand side one, we can negate both sides and then take the square root. That would just give us x equals 0. Right-hand side, what we would have to do for this one is we would have to cube root both sides, but that would just give us x minus 2 equals 0, which would just give us x equals 2. So let's figure out the multiplicity for each one. So what we have to do is we have to look at the exponents on the factors. So here's one exponent, here's the other exponent. So this means it's going to be, for x equals 0, since it was a 2, that's going to be even multiplicity. That means at that x-intercept, it's going to touch it, the x-axis, and turn back. For x equals 2, we had a 3 as the exponent, which is going to be an odd number. So this has odd multiplicity, which means it's going to completely cut through the x-axis at x equals 2. So we have x equals 0, x equals 2. Could also consider end behavior here, and we could graph it pretty accurately. So it's going to touch 0, it's going to turn around, and then it has to cut through at x equals 2. So it would look something like that. Okay, so that's what multiplicity means. It's determining what the behavior is at the x-intercept. Let's do a couple more. So g of x is 1/2 times x plus 1 times 2x minus 3 squared. So we're going to set this equal to 0. So 1/2 times x plus 1 times 2x minus 3 squared equals 0. So this is already factored for us again. So we can just set those factors to 0. So don't make the mistake of accidentally setting 1/2 to 0 and saying, oh, x equals 1/2 is a x-intercept. That would be super wrong. It's just a constant, so I'm going to bring it with the first one, with the first factor here. And then set the other factor to 0. So what we can do on this left-hand side, we can multiply both sides by 2 to cancel the 1/2. We'd end up with x plus 1 equals 0. Subtract 1 on both sides, we get x equals negative 1. Right-hand side, square root both sides, we get 2x minus 3 equals 0. Add 3 and then divide by 2, we get x equals 3 over 2. So looking at the multiplicity, the one on the right has an exponent of 2 on the factor. So this is going to give us even multiplicity at this x-intercept. So what we could say is that it has multiplicity of 2. And the one on the left here, there's a little exponent of 1 that's not written. So that means it has odd multiplicity. Okay, and let's graph these on here. So we have negative 1 and 3 over 2. 3 over 2 is 1.5. So it's going to completely cut through at negative 1. And it's going to turn back for x equals 3 over 2 and touch it. And then turn back the way that it came. Once again, I know how I'm graphing this with the end behaviors based on the leading coefficient test. Okay, so let's do a couple more here. So we have h of x is x times x minus 4 squared times x plus 2 cubed. So we're going to set it equal to 0. So we're setting this whole thing equal to 0. I'll go a little bit faster here. So it's already factored once again. So that means either x is 0 or x minus 4 squared is 0, or x plus 2 cubed is 0. So solving all these separately, we already have x equals 0. We would get x equals 4 for the second one, x equals negative 2 for the third one. So let's look at the multiplicities. For x equals 0, there's just a coefficient of, there's just an exponent of 1 there, which is odd. So this is odd multiplicity. X minus 4 factor has an exponent of 2, so this is has even multiplicity. And for x equals negative 2 has an exponent of 3 on the factor, which is odd multiplicity. Okay, so let's plot these down real quick. We got negative 2, 0, and 4. So we know it cuts through at negative 2 because it was odd multiplicity. And then it's going to cut directly through at 0 because of odd multiplicity once again. And then at x equals 4, it had even multiplicity, so it's going to come back, touch it, and then bounce back. Okay, let's maybe do 2 more. So f of x is 3x cubed minus 6x squared plus 3x. So setting these finding these x-intercepts, setting the function equal to 0. So this time you probably realize 3x cubed minus 6x squared plus 3x is not factored. So we have to factor it. And this is going to be using GCF. So I'm going to factor out a 3x here. And we're going to be left with x squared minus 2x plus 1. We can factor that quadratic. Two numbers that multiply to 1 that add to negative 2. That would be x minus 1 times x minus 1. And just like before, I'm going to write that as x minus 1 squared. Okay, so now it's factored, so that means either this factor has to be 0 or this one has to be 0. That's going to give us x equals 0 on the left and x equals 1 on the right. So let's look at their multiplicity now. So for 3x equals 0, 3x has a exponent of 1 up there that's not written, which means it has odd multiplicity. And then x minus 1 squared has an exponent of 2, which means it has even multiplicity. So we go to 0, put a dot, go to 1, put a dot. So it has to cross through 0, but then turn around and touch 1 and bounce back. Okay, one more and then we'll get to graphing and get to how I'm actually going through and graphing these. So h of x, x cubed minus 3x squared minus 9x plus 27. Take it, set it equal to 0. So this one, it looks like it's going to be grouping. So it's grouping, so I'm going to skip to the end here just because we did a couple of grouping ones. What we should end up with, I'll put dot, 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 just so we know where I'm skipping some steps. We should end up with x minus 3 squared times x plus 3 equals 0. I'm going to leave that to you guys to check if you want, to make sure I didn't mess anything up. So we're going to set both of them to 0. From the first one, we get x equals 3. Second one, we get x equals negative 3. So for this first one, we have a 2 on the exponent, which is going to give us even multiplicity. X plus 3 is raised to the first over here, which means odd multiplicity. So we have negative 3, positive 3. We can use the end behavior. We know it cuts through at negative 3. and then it's going to come back and touch at positive 3 and bounce back for the even multiplicity. And this is h of x. Okay, so that's multiplicity and x-intercepts. So next, let's do turning points. So for turning points of polynomials, turning points, if a polynomial is degree n, that means the graph of the polynomial has at most n minus 1 turning points. So a turning point is when the function changes from increasing to decreasing or vice versa. These are also called relative maxima or relative minima values. So it's like the tops of the hills or the little bottom of the valleys on the graphs. So for example, let's say at most, how many turning points does f of x equals x to the 5th minus 6x cubed plus 8x plus 1 have? So this is a degree 5 polynomial, right? Degree 5. So what this means, this has at most 5 minus 1, so it has at most 4 turning points for this graph. So it doesn't have to have 4, but it has at most 4. So what this means, it might look something like this. So we would say that there is a turning point here, here, and here. So that's 4 turning points. So at most 4 turning points. Obviously, I just kind of freehanded that and drew that quickly, but that's what the turning points mean. Okay, so that's probably the easiest step that we'll be doing for this, for graphing these. Okay, so we're almost to the actual graphing part. I think there's like one more thing, and that is the symmetry. So symmetry of a graph. So there's either going to be, the way that we're doing it, this isn't the only type of symmetry. There can be y-axis symmetry, or there can be origin symmetry. Y-axis symmetry means it is an even function. Mathematically, that means f of negative x would equal f of x. So for example, let's say we had something like f of x equals 2x to the 4th minus x squared plus 1. So what we would try to do is we would see what is f of negative x. So you'd plug in a negative x everywhere there's an x. And then you would simplify it. Negative x to an even number is just positive x to an even number, because the negatives will cancel out when they're grouped in evens being multiplied. So this would just be 2x to the 4th. Negative x squared is positive x squared, but it's still going to be minus because there was a minus in front of it. So what we have right here, 2x to the 4th minus x squared plus 1, is actually the same thing as just f of x, right, from what we started with. So since f of negative x equals f of x, that means it is an even function with y-axis symmetry. So if we were to graph it, it would look something like this. Not even sure if this is 100% accurate here, but you could see that it's a mirror image of itself over the y-axis. So the function evaluated for a positive x is going to give us the same value if we evaluated it for the negative x. Okay, for origin symmetry, what this means is that it's a 180-degree rotation of itself. We call these odd functions, and that means f of negative x equals negative f of x. So 180-degree rotation of itself means if we took the page and flipped it upside down, it would look exactly the same as it did before we flipped it. So for example, let's say we had f of x equals x to the 5th plus 3x cubed. So we're going to start the same way that we just did it. We're going to plug in a negative x, and then we're going to simplify it. So that's negative x to the fifth plus 3 times negative x cubed. A negative to an odd number is going to be the same thing if we drop the parentheses and raise it to that odd number. So it's going to be negative x to the fifth minus 3x cubed. So what we have to do for this one is we have to recognize that that is not equal to the regular function. So if we factor out a negative, we're going to end up with negative and then in parentheses x to the fifth plus 3x cubed. So now what is in those parentheses is our original. So this is equal to negative f of x. So since we got f of negative x equals negative f of x, that means this has origin symmetry. It is an odd function. So if we were to graph this, not really positive if I'm graphing this super accurately or not, but it might look something like this. So that would be the function. So notice that if you flipped your laptop over 180 degrees, it would look exactly the same as what it looks like before you flipped it over. So that means origin symmetry, 180 degree rotation of itself. Okay, and then that's the only symmetry we're really going to be looking for with polynomials. If the function is neither even nor odd, then it just has neither of those symmetries. So there's a shortcut. The shortcut is written down here. So here's a shortcut. If all exponents are even, so every exponent, if it's even, it's an even function with or without the constant term. So the constant term won't throw off the symmetry for even functions. That's because that's just essentially a vertical shift up or down. That won't affect y-axis symmetry. If all exponents are odd on each term, then it's an odd function. So the thing you have to look out for here is only if it does not have a constant term. So the constant term will throw off odd symmetry. And then if there is a mix of even and odd exponents, then it has neither symmetry. So I'm going to be using this shortcut to do these problems on the next page. So let's determine the following symmetry for these functions. So the first one is 6x squared plus 5. So we have an even exponent of 2, and then we have a constant. So that means it's going to be an even function, so it has y-axis symmetry. So the reason why constants don't throw off the symmetry for y-axis symmetry is because we can make it have a variable of x with an exponent of 0. X to the 0 is equal to 1, right? So throwing that in there doesn't change anything. 0 can be thought of as an even number, meaning that's an even exponent. Okay, for the next one, we have g of x is x cubed minus 2x squared minus x plus 1. So we have a mix of exponents here. We have a 3, 2, 1, and 0. So this is going to be no symmetry. Or let me put neither symmetry just to be a little bit more accurate here. Next one we have h of x is negative x to the fifth plus x cubed minus 2x. So we have an exponent of 5, 3, and 1. So this is an odd function with origin symmetry because all of those exponents are odd. And lastly here we have p of x, which is 8x to the 7th plus 3x cubed minus 4x minus 2. So we have odd exponents. We have 7, 3, 1. The one that throws it off is the constant term because once again that's x to the 0. So that means there's a mix of exponents, so there's going to be neither symmetry here. Okay, so now let's get into graphing it using everything we just did. So here are the kind of general steps for graphing polynomials. So we're going to determine the end behavior, which once again is the leading coefficient test. We're going to find the x-intercepts by setting the function equal to 0 and solving for x. And then also in that same step, determine the multiplicity, which that's usually going to be the only step that is long. Third step, we're going to find the y-intercepts by evaluating f of 0. Step 4, we're going to determine the maximum number of turning points. 5, if there's any symmetry, what we just did. And then 6, we're just going to plot all of those points and then connect them with a smooth continuous curve. Make sure you have arrows on the end of the graphs also. Okay, so let's do a couple examples. So for the first one, we have graph f of x equals x cubed plus 3x squared minus x minus 3. So let's first find the end behavior. So the end behavior is going to be based off of the leading term, which is x cubed. And this is an odd exponent and a positive coefficient of positive 1 out front. So odd exponent, positive coefficient, what that means is it's going to fall on the left and rise on the right. So I'm not going to write it out, I'm just going to draw it out. Okay, next thing, let's find the x-intercepts and the multiplicity. So I'm not going to go through and show every single step for this just because we've seen me do it a million times already. I'm probably getting sick of it. So let's do the x-intercepts, which means we're setting it equal to 0. So this is going to be x cubed plus 3x squared minus x minus 3 equal to 0. So this is going to be grouping. Obviously, I recommend that make sure you know how to do this. I recommend going through and making sure you can group it real quick and factor it correctly. What we would end up with is x plus 3 times x plus 1 times x minus 1. So that's from grouping. So we're going to set all of these factors equal to 0. We're going to get x equals negative 3 for the first one, x equals negative 1 for the second one, and x equals positive 1 for the third one. So now when we're going up to the factors, or for the exponents, for the multiplicity, each one of these factors only had an exponent of 1, right? 1, 1, and 1. So this means that all three have odd multiplicity. Okay, and then for the next thing, let's do, so we know that at each one of those x-intercepts, negative 3, negative 1, and 1, it's completely crossing through the x-axis. So now let's do the y-intercept. There's always going to be just one y-intercept, because if there wasn't, then it wouldn't be a function. So we need to evaluate f of 0. So we're going to plug in a 0 everywhere in the function that there's an x. So it's going to be 0 cubed plus 3 times 0 squared minus 0 minus 3. Everything is going to cancel, so it's just going to be left with that negative 3 at the end. Let me go back up here now for the max number of turning points. So max turning points is probably the easiest one. That's just going to be n minus 1. This is a degree 3 polynomial, so that means it's going to be n minus 1, so 3 minus 1. So there's going to be 2. There's going to be 2 maximum turning points here. And 5 for symmetry, we can use the shortcut. You won't always be able to use the shortcut for every single type of function by any means. Polynomials, you can always use the shortcut though. Just make sure it's expanded out. So symmetry, there's a mix of exponents here, right? There's a 3, 2, 1, and constant term. So there's going to be neither there's going to be neither y-axis symmetry or origin symmetry. So I'm just going to put neither symmetry. In step 6, plot some points. So obviously don't have to write that. Just going to start plotting them. So let's plop down these x-intercepts. Oops. So we have -3, -1, and +1. And let's plop down that y-intercept. The y-intercept is -3. So now I'm going to use the end behavior here. So the end behavior, we said it falls to the left and rises to the right. So I'm going to go to the leftmost x-intercept. We know it's going to fall. And then the rightmost one, we know it's going to rise. And now it's pretty much connect the dots, making sure your multiplicity is correct. So it crosses through all of these. So it crosses through, it has to come back to cross through that one, has to go through that point, and has to go through that point. So it's pretty much just connect the dots, making sure your multiplicity is correct. And that is the function. The only thing that we don't have completely accurate is if you see this little maximum value right here, that turning point, I'm not positive that that's at the correct point, but that's okay. Just has to be decently accurate. Okay, so let's do the next one. So we have f of x equals 2x to the 4th plus 8x cubed plus 8x squared. So for this one, let's start off the same way, let's find the end behavior. So we have to find the leading term. So the leading term is 2x to the 4th. So this is going to be an even exponent and a positive coefficient. So that means it's going to rise to the left and rise to the right. So even exponent, positive coefficient, I think of y equals x squared, so it's parabola opening upwards on both sides. So next, let's find the x-intercepts. So we're going to find the x-intercepts and the multiplicity. So setting it equal to 0. So 2x to the 4th plus 8x cubed plus 8x squared equals 0. So once again, I'm going to skip to the factored version. This is going to be using GCF, and then it's also going to be factoring a trinomial, factoring the quadratic afterwards. So we're going to end up with 2x squared times x plus 2 squared. We're going to set both of those to 0. And then solve for x. So on the left-hand side, divide by 2, take the square root. Just x equals 0. On the right, square root both sides, subtract 2. We get x equals -2. Okay, and then for the multiplicity, we have to look at the exponents. On the factors, we have a 2 up there, a 2 up there, so both have even multiplicity. Which means for both of them, it's going to touch the x-intercept and bounce back the way that it came. It's not going to completely cut through it. Okay, next for the y-intercept. So we're going to take the function, what's the function here? And we're going to plug in a 0, so we're going to evaluate f of 0. So it's going to be 2 times 0 to the 4th plus 8 times 0 cubed plus 8 times 0 squared So everything cancels here, and we're just left with 0. And next, let's look at the maximum number of turning points. Once again, this one's going to be pretty easy. It's just going to be n minus 1. This is a degree 4 polynomial, so 4 minus 1. So at most, there's going to be 3 turning points here. And for the last step, for the symmetry, let's go back up here. So there is a mix between even and odd exponents. We have 4, 3, and 2. So once again, just like before, that means this has neither y-axis nor origin symmetry. Okay, so let's graph it. So we're going to have, let's graph the x-intercepts here of 0 and -2. And then let's graph the y-intercept of 0, which is already right there because it was at the origin. And let's see, what else do we have here? So let's use, I guess we can just graph it now. Let's use that m behavior. So it's going up on both sides. It's rising on both sides. So we know it's going to be rising after that one and rising after this one. And now let's look at the multiplicity and fill in the gaps here and connect the dots. So it has to come down and touch it and bounce back because it was even multiplicity. The next one also had even multiplicity, so it has to do the exact same thing. And that's it. So that's going to be our function. That is f of x. Okay, let's do a couple more to make sure we're good. So for this one, we have f of x equals -2x times x minus 1 squared times x plus 2. So let's determine the end behavior. So the leading, so it gets a little harder for these ones. The leading term, I'll write this one down. So this one's already factored for us, which makes finding the x-intercept super easy, but finding the leading term is a little bit more difficult. The leading term is going to be the leading term in this first term times the leading term in the second one times the leading term in the third one. So it's going to be -2x times x squared, because it was a squared factor, and then times x. So the leading term here is going to be -2 times x squared times x, so -2x to the 4th. So a little bit hard to figure that one out. So now we have a even exponent of 4 and a negative coefficient of -2. So even exponent, negative coefficient, it's going to fall on both sides. Okay, so next, that's probably one of the hardest parts for this particular question. Next, x-intercepts and the multiplicity. So that's going to be setting it equal to 0. So this is nice because we have to do absolutely 0 work factoring it because it's already factored for us. So it's going to be -2x times x minus 1 squared times x plus 2 equals 0. And now just set all of those factors equal to 0. So the first one, we have -2x equals 0. Solve that for x, we get x equals 0. Then we get x minus 1 squared equals 0. Square root both sides, we get x equals 1. And then add the 1. And then x plus 2 equals 0. Gives us x equals -2. Okay, so for the multiplicity, this first one over here on the left has an exponent of 1. So this has odd multiplicity, so we know that it's crossing through the x-axis at that point. For x equals 1, it had an exponent of 2 on its factor. So x equals 1 has even multiplicity. So we know it's going to touch it there and bounce back the way that it came. For x plus 2, that has an exponent of 1. Highlight all those. So we know that this one also has odd multiplicity. So it's crossing it at x equals -2. Okay, next for the y-intercept. And we're going to evaluate f of 0 again. So maybe just a little more work than usual with this one. So plugging in a 0, -2 times 0 times 0 minus 1 squared times 0 plus 2. This whole thing is going to be 0 because of that second number, that second right after the -2. That's a 0, multiplying everything, so it's 0. And next, for the max number of turning points. So max number of turning points, so once again, this is going to be n minus 1. So we said the leading term was -2x to the 4th. That means this is a degree 4 polynomial, so 4 minus 1 equals 3. So maximum 3 number of turning points. And then lastly for the symmetry, let's see. So this one's a little bit harder with the symmetry. I'm going to leave this to you guys to do just so I don't have to waste more time. It's already a very long section. You can expand that out. So if you expanded out that whole entire polynomial and distributed everything, combined like terms, you would see that there's going to be neither symmetry. There's also another way, another different way. If we look at the x-intercepts here, our x-intercepts were 0, 1, and -2. Those are not symmetric x-intercepts. So there's no way we can plop those down here. So let's see, write them down. So we have -2, oops, and 0, and 1. No matter what we try, we can never get this to be y-axis symmetry or origin symmetry, because they aren't symmetric. Okay, so now let's fill in the rest of the stuff here. So let's look at the end behavior. So it's falling on both sides. So that means I'm going to go over here to the leftmost point and make it falling. Go over here, make it falling, and then connect the dots using the appropriate multiplicity, as well as the max number of turning points. So the multiplicity at -2 is odd. So we know it's cutting through. At 0, we said it was odd, so it's cutting through. I believe we said it was odd, yep. So it's cutting through, and then at 1, we said it was even. So it's touching it and bouncing back. So obviously not perfect, because there's not really... I'm going to erase that, actually. Okay, there we go. Looks a little better now, and that is our function f of x. So it does have a maximum, it does have 3 turning points, 1, 2, 3. Okay, so let's do, I believe this is one more. Yep, one more, and then we'll do one more small thing, and then we'll be good. Okay, so let's say we have f of x is x cubed plus x squared minus x minus 1. So the end behavior here. The end behavior, we have the leading term is x cubed. So it's going to be an odd exponent and a positive 1 coefficient, so positive coefficient. So that means it's going to fall to the left and rise to the right. And then next, x-intercepts and multiplicity. So before even doing the x-intercepts here, we can see that we have a degree 3 polynomial. And we have all four terms, so automatically I'm thinking grouping. It's not always going to work, but it's a good place to try. So set it equal to 0. So once again, I'm going to skip it. I'll skip right to the factored version, but I'll write down what I did, the method. So when we group this, what we end up getting is x plus 1 squared times x minus 1 equals 0. So we set them both equal to 0. We get x equals negative 1, and we get x equals 1. From x equals negative 1, that was a multiplicity of 2, so that's an even multiplicity. And x minus 1 equals 0, giving us x equals 1, had an exponent of 1 there, which means it has odd multiplicity. Okay, so that part's done. So that's pretty much the only hard part once again. So next thing is the y-intercept. So we plug in a 0. So we evaluate f of 0. And we get 0 cubed plus 0 squared minus 0 plus 1. What is that, minus 1? So we get negative 1 is our y-intercept. Yep. Okay, and then for the next thing, for the max number of turning points, this was a degree 3 polynomial. So n minus 1, that's going to be 3 minus 1, so there's going to be at most 2 turning points. And lastly, for the symmetry, once again here, there's going to be no symmetry because we have a mix of even and odd exponents. So there's going to be neither symmetry. Okay, so let's graph it. So we plot the points for the x-intercept, negative 1 and 1. We have a y-intercept of negative 1. And let's use the end behavior. We said it was falling to the left and rising to the right. So now we connect the dots based on the multiplicity. X equals negative 1 was even multiplicity and x equals 1 was odd. So it has to touch at negative 1 and bounce back, go through the y-intercept, and then it's cutting through x equals positive 1. And that is our function f of x. Okay, so one more thing. The intermediate value theorem, which we can abbreviate IVT. So this theorem is actually really powerful. This intermediate value theorem, it tells us where we can find x-intercepts. So it doesn't tell us what they are, but it tells us essentially where they are between two different points where we can find them. So the intermediate value theorem says if f is a polynomial, so the function's a polynomial, that's really, really important. I'll bring that up back in a second. If the function evaluated at A and the function evaluated at B have opposite signs, meaning one's positive and the other one's negative, there has to be at least one value, which we'll call C, between the x values A and B such that f of C equals 0. F of C equals 0, that means this is the x-intercept, right? So they're saying if two y values, one's positive, one's negative, there has to be an x-intercept between them, which hopefully just kind of makes logical sense. So let's kind of see why it should make logical sense when we look at the graph. So let's say we have 2 points. Let's say B is right here and A is over here somewhere. And let's say f of A is down here. So So this would be f of a. And let's say f of b is up here. So this would be f of b. So it's just the y value for a, y value for b. So if we connected these dots, let's say it was supposed to be a polynomial, so oops. So let's say it looks something like this. Then there's a value right here in this case. And that value is c, such that f of c is 0, meaning there is an x-intercept at c. So that should seem obvious. It's just saying to go from positive or negative or vice versa, it has to go through the x-axis. So the reason why this is important that it's a polynomial is because polynomials are continuous. So we know it's not jumping over the x-axis. It has to cut right through it. So what we could say here is f of a is negative and f of b is positive. So by the intermediate value theorem, we must have a c value such that f of c is 0. Okay, so let's do an example. Just do one example. So let's show that f of x equals x cubed minus 2x minus 5 has a real 0 between x equals 2 and x equals 3. So what that is saying is that that function has an x-intercept between x equals 2 and x equals 3. So what we have to do is we have to show that f of 2 and f of 3 have opposite plus or minus signs. So one's going to be negative, one's going to be positive. So let's evaluate them. So let's find f of 2. So we're going to plug in a 2, so it's going to be 2 cubed minus 2 times 2 minus 5. That's going to be 8 minus 4 minus 5, which is negative 1. And then evaluate f of 3. So that's going to be 3 cubed minus 2 times 3 minus 5. That's 27 minus 6 minus 5 is 16. Okay, so taking a look at what we got here, f of 2 is negative and f of 3 is positive. So I'm going to write this out like a good kind of conclusion here. So since f of x is a polynomial, if it's not a polynomial, we can't even really mention this unless it's continuous over that interval. So since f of x is a polynomial, and f of 2 and f of 3 have different signs, one's positive, one's negative, by the intermediate value theorem, f of x must have a 0 which once again means x-intercept, which must have a 0 between x equals 2 and x equals 3. Okay, so it's not too bad for those problems. That's pretty much all there is to it. Okay, so long section, but that is all for 3.2.